Hello, and welcome to the fifth lecture on quantum computing. Today we're going to talk about classical bits and quantum bits, specifically the differences between classical and quantum bits. Classical bits being those used in a classical computer or those a classical computer operates on, and quantum bits, of course, being the ones that a quantum computer operates on. And anytime in my lecture slides you see C bits here, I refer to classical bits. And that's what we start with, classical bits and their states. So as you know, a classical computer operates on strings of bits. So each bit can take the value 0 or 1. And while I do a computation on a classical computer, I can always look at the intermediate result. It makes no difference. I can always stop the computation, look at it, and I don't lose anything except time in that case, but I don't lose any information. So that's important. It's different with quantum computers because here looking means you disturb the state, this rich state of superposition that we already talked about before, and that results in a collapse usually. So, or you end up with only one state. So all this rich information that you had in your superposition, so for example, possible solutions to your problem, that's all lost once you look at it. So you better make sure that once you look at it, you are done with the evolution of your system or the algorithm. Classical computers convert strings of bits into other strings of bits. So anytime we write code, then the most fundamental level, the computer operates on strings of bits, so converts it to the machine language, strings of bits, and changes it from one string of bits to another string of bits. And there's a collection of physical systems associated with distinguishable states of zeros and ones. So for example, a switch or magnetization. The representation of states. So if we talk about how you write down the states or denote the states, then if we have 5 classical bits representing 11001, then the state of all bits, all 5 classical bits, in terms of the Dirac notation that we talked about before, can be written in that way. Okay, so where you have single for each of the single bits, a separate bracket around them. Possible states of a pair of C bits. So as you know, we not only operate on single bits, so no matter if they're classical or quantum, usually we operate on multiple bits. And so what you see here are the possible combination for a 2-bit system. And this means in vectorial representation, since we're talking about orthogonal vectors, we have 4-dimensional bit space. Okay, so 3 C-bit states, this is just a generalization and generalizes to n C-bit states, can be written as before, but it becomes cumbersome to write it down or to give it to give each single bit a bracket. So very often we just refer to that one, or make it even simpler and use the subscript notation as we see here. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Here we're talking about the possible 3-bit states, and since we're talking about 3 bits, we can denote that with a subscript here, so it makes it easier to write it down. Okay, and very often we also talk about shared bits, so specifically important when we later on, in terms of quantum bits, talk about entanglement. Very often we talk about Alice and Bob's shared bit, which you can denote with subscripts again. So here this refers to first bit belongs to Alice, second bit belongs to Bob. And as I said, this will become really interesting when we talk about entanglement. We also have the vectorial representation, so you know both the bracket notation and the vectorial representation, as I indicated in one of the last lectures. This really is just a name. It doesn't say or not necessarily says anything about the vectorial representations or whatever makes it easy for you, that you could use as a name, but the usual convention is, if we're talking about computational basis states, that we do it in one of the ways we specified before. We also talked about the vectorial representation. For the state 0, it is 1, 0. For the state 1, it is 0, 1, which generalizes to 2-qubit states as we had before. Or C-bits in that case. The 2 C-bit vector space is 4-dimensional with an orthonormal basis. So remember last time we said that orthogonality is one condition, so we need to be able to distinguish the states. So we're each of the states represents one axis in a coordinate system, and then the other condition is that the vectors have unit length, and any operation that we carry out on one of these vectors must be a unitary transformation to preserve unit length. So we can't change the length of a vector, because again, this would not result in any meaningful state. Or more formal in that case as a tensor product. So just to remind you how we can figure out from single qubit states what the combined state is. So here in that case we have 2 times or 2 qubits or 2 c-bits in the state 0, and if we want to generalize to 2 qubit space, which is 4-dimensional vector space, we just execute the tensor product, and in that case end up with 1, 0, 0, 0. Okay, so and the same of course holds true for the other states. So we'll have a single 1 in each of these vectors. The tensor product AB of an M component vector with components A sub mu and an N component vector B with B sub V is the Mn component vector with components indexed by all Mn possible. If we now look at 3 qubits, X, Y, and Z, then you can construct a 3 qubit state by executing a tensor product between these 3. So fairly straightforward. If you look at the first row here, it's given by X sub 0, Y sub 0, Z sub 0. Second row is given by X sub 0, Y sub 0, Z sub 1, and so on. So that generalizes to N classical bits, of course, then also qubits. So even though the representation of classical bit states by column vectors may give a natural description of multi-bit states, for almost all other purposes it's better and simpler to deal directly with the state vectors in their abstract forms, the ones that we already got to know previously. In quantum computing also, when you want to execute your computations, you usually do that in bracket notation. Or you can do that in bracket notation, you don't have to, and see how transformations work. So that makes your life a lot easier. So one important part in the quantum magic is also that we do reversible operations. So reversible operations transforming the initial states of the qubits into its final form. And we do that, as indicated, with processes, only processes that can be inverted. Only one single irreversible operation exists in quantum computing, which is called the measurement. So we talked about that previously. It's not reversible because once you execute your measurement, you extract, so to say, one final state, one definite state. So what you do is, from the superposition of states, you end up with one state, and this is irreversible. So there is no way from this final state to reconstruct this superposition of states that you were in before the measurement, or the system exhibited before measurement. And measurement is the only way to extract useful information from the qubits after the state has acquired its final form. So therefore, needs to be done. There is no way around it if you want to get some meaningful result. The measurement in quantum computing is also non-trivial and crucial, whereby in a classical computer, the extraction of information is fairly straightforward. So it's not even viewed as an inherent part of the computational process. The only computationally relevant operations on a classical computer that can be extended to operations on a quantum computer are those reversible. Those that are reversible. So only operations that are reversible on C-bits are of interest for us. In a reversible operation, any final state arises from a unique initial state. So that's important to remember. And one example for an irreversible operation in our case is the erase. So you imagine you start with a classical bit, only one bit in either 0 or 1. If you execute the erase operation, the classical bit will end up in the state 0. So there's no way from this final state of telling which the original state was. So there is no way of telling if it was 0 or 1. So therefore, this operation is not reversible. And it's impossible to recover the initial state. The only non-trivial reversible operation to a classical bit is not. So usually denoted by X, we also denote it by X in quantum computing, and it interchanges the states 0 and 1, so flipping the bit in that case. So X applied to the state vector X, or not operation applied to X, gives you not X. So that means 1 becomes 0, 0 becomes 1. It is reversible, so which can be denoted that way. So if you apply it twice, you get back the original state. And if you execute the matrix multiplication, then you would get the identity matrix, so which also tells you that it's reversible. So we can look at that example here on the bottom. So if we look at that X transformation, which is given by this matrix here, so if we execute that 0 times 0 plus 1 times 1, then we have 0 here, we have 0 here. So that gives you the identity transformation if you do that calculation. If we just look at it again from a vectorial perspective and matrix, linear algebra perspective, if you execute 0, the not operation on the state 1, for example, then 0 times 0 plus 1 times 1 gives you 1. And here we have 0, which means it transforms the state 0 to the state 1. And if we apply it again, of course, you may try, then you will get back the original 0 state. The two reversible things in the sense of not on a single C-bit, classical bit, correspond, therefore, to X, which is the not transformation, and the identity operation. Okay? So we have richer possibilities for reversible operations when working on multiple bits, be that quantum or classical bits. The most general operation on two classical bits is any permutation of their 4 possible states. And the simplest non-trivial example that we look at here is the swap operator S sub ij, which simply interchanges the states of the qubits, the C bits I and J. It is given by the matrix that you see here on the bottom, and what it does is it interchanges from the state 0, 1 to 1, 0 and vice versa, but it leaves the states 0, 0 and 1, 1 alone. So let's see how we get to that operator. So let's write it down again first. So we have the operator Sij, which is given by this matrix here. But how do we get to that one? So remember how we did it the last time. So we take our state, initial state, 1, 0, and the target state, in that case, 0, 1, and we create the matrix. But for this, we need, what we need is the vectorial representation. And just as a reminder, let's do that once more. So we take the 0 vector, 1, 0, and create the tensor product with the 1 vector here, which then gives us 0, 1, 0, 0. We do the same here for 1, 0, where we start with the vector 1, create a tensor product with 1, 0, which gives us 0, 0, 1, 0. And now, if we look at what we have here, we have the column vector of 0, 1, which is given by 0, 1, 0, 0. And we have the row vector of 1, 0, which is given by 0, 0, 1, 0. So then we create the matrix out of that, which is 0 times 0 and so on. So the first row will be all zeros. The second row will be all zeros except that one here. Third row will be all zeros, and fourth row will be all zeros as well. Okay, so now we have the first part of that. Now you do the same for this one here. So I write it down here on top. So you do the same for that one. You may try that out. But the matrix representation of that one is all zeros here. 0, 0, 0, 0. Then we have 0, 0, 1, 0. Okay. Now we take this one here and we add them up, which results in Sij, which is again given by 1, 0, 0, 0, 0, 0, 1, 0. Okay, and now we apply it to the state 1, 0, or let's apply it to the state 0, 1 first. So we take 0, 1, 0, 0 here, and if we multiply that out again, so we get 0 for the first row, so we have 0 times 0, 0 times 1, 1 times 0, 0 for the second row, so we have 1 here in the third row. Okay, and that one is the state 1, 0. So clearly you see it transformed 0, 1 to 1, 0. That's how the swap operator works and how you get to that operator. One operator that is very important in quantum computing is the controlled NOT operation, C sub ij. So what it does is if the state of the ith bit here, in that case again classical bit, if that one is 0, it leaves the state of the jth qubit or c bit alone. However, if the state of the control bit is 1, then it applies the NOT operation to the state of the target bit. Okay? And the state of the control bit is left unchanged in either case. So how you can look at it is a modulo operation as well. So let's say this controlled operator here, C10, denotes that the first one is the control bit, the second one is the target bit. So you have the two bits X and Y. And what you could do is, or how it changes that state is, it leaves the control bit alone in that case, so X remains X. But to the target bit, it applies the modulo operation, so it's XOR. So it's the modulo operation that you see here, which would mean in that case, so assuming Y is in the state 1 and X is also in the state 1, it adds it up. 1 plus 1 divided by 2 results in 0, setting the second one to 0. So 0 remainder in that case. So if it were differently, if the first one would be 1 and the target bit would be 0, then you would also add it up. 1 plus 0 divided by 2, you have 1 remainder, so sets the target bit to 1. Okay, that's how that works. And of course it also works with the second one as control bit and the first one as a target bit. And this symbol here is just the modulo operation, so it denotes addition modulo 2. And as we just said, called exclusive OR, which you probably know from computer science. It's also interesting that sometimes you can combine multiple operators to create a new one. So swap, for example, can be created out of 3 controlled NOT operations. You may try. You'll see the matrix of the controlled NOT operation, or first one here is the control bit, is given by that matrix. And we can look at it again. So let's say we have the state, that's the state 1, 0, which we remember, we just give the vector here 0, 1, tensor product 1, 0, and 0 times 1, 0 times 0, 1, 0. So that's the state. If we execute the controlled NOT operation on 1, 0, the result should be 1, 1. So let's give that a try. So we have 0, 0, 1, 0 here, and we run through that. First one is 0, second one is 0, third one is 0, and the fourth one, 0 times 0, 0 times 0, 1 times 1, 0 times 0 gives you 1, which is the state 1, 1. So it works. And you may try with some other operations. So for example, try it out with 0, 1, or try it out with 1, 1. It will leave the states where the control bit is 0 alone, and it will change the states of the others. Okay? So if the control bit is on the right, and the controlled NOT operation interchanges 0, 1 and 1, 1, and 0, 0 and 1, 0 remain fixed. And you may try again. So if you just remember how we constructed the swap operator, just give it a try and look at if you can construct the controlled NOT operator based on the initial and target states that we have at hand. So a very common kind of 2-bit operator in general consists of the tensor product of 2 1-bit operators. And remember, we looked at some of these before. Remember when we talked about the identity? So we said sometimes we just want to execute an operation on a 2-qubit state, which of course generalizes to n qubits, but we don't want to do something to all the bits that we have in our string. So what we really want is manipulate some and leave others alone. And sometimes that may work with an identity transformation. So let's say you have 4-dimensional 2-qubit space. You also need 4-dimensional matrices to operate with these matrices on the qubit state, on the 2-qubit state. So which then means you create your transformation if you want to leave the second one alone, for example, such that the first one is your unitary that does the job on the first one and the identity on the second one. So that's how you construct it. But of course, that's not the only way. So this is just a very general summary on the abstraction of what we want to do. Okay. Another 1 C-bit operator is the projection operator. And the projection operator onto the state 1 or the projection operator onto the state 0. You remember we looked at this before, so you can construct the projection operator for the state 0 by taking the outer product of 0, which in that case would be 1, 0, 0, 1, 1, 0, 0, 0 here. And for the projection operator for state 1, you do the same, only you take the state 1 and create the outer product out of this state. It has some interesting properties that you can see here. And n plus tilde n that you see here, which is the both projection operators, give you the identity, of course. Okay. Now let's make a quick excursus on eigenvectors and eigenvalues. So if an operator acts on a ket, the result is a new ket. So here we have an operator A acting on ket psi, which gives you a new ket chi in that case. So it's easier if we work with eigenvectors and eigenvalues. So if we look at this vector, so psi, then it is an eigenvector of the operator A if A is a complex constant. So this is supposed to be a small a is a complex constant resulting or producing, so application of the operator A on the vector psi gives you the same psi multiplied by a constant. Okay, so if that happens, then psi here is an eigenvector of this operator and A is an eigenvalue. So remember we looked at that before, eigenvalues or scalar values in terms of the Schrödinger equations. So although there may be A may be a complex constant, the eigenvalues of Hermitian operators are always real numbers, and its eigenvectors are orthogonal. We remember how we define orthogonality. So if you remember the single qubit states, we just try it out and see how they are orthogonal to each other. Why is that easier? Well, if an operator acts on its eigenvectors, the result is the same eigenvector times its eigenvalues. So that means no change of states happens and there is no requirement to do calculation with another state vector. So if you remember that dice operator from before, which acts in 11-dimensional space and is Hermitian, its features are 11 orthogonal eigenvectors and 11 eigenvalues. So if we look at that operator again, you remember we defined it to be this matrix, and the unit vectors in the 11 different directions, so they are orthogonal to each other, so they may serve as eigenvectors. And you remember the scalar, so if we go back to that matrix, so in that case here it would be 2, okay? So it would be your eigenvalue. So the eigenvalues are the numbers resulting from applying W on an eigenvector. In our case, as just said, it would be 2, 3, 4, and so on, up to 12. And the eigenvectors of a Hermitian operator form a complete set of orthonormal vectors, a complete basis in the state space. So and if we consider this eigenbasis, the operator in matrix representation is diagonal, and the elements along the diagonal are eigenvalues, which is the main reason for working with them. Remember the computational basis states that we work with. Remember two-dimensional qubit space, for four-dimensional 2-qubit space, for example, then these are also the eigenvectors that we're dealing with here. So considering an initial operator, W, as given by that operator here in that slide, then a change into the basis of the operator's eigenvector diagonalizes the matrix into the form of W we already know. So eigen is the component of the word eigenvector, as these form a natural basis for the operator. One more thing with regard to describing them. So if two or more eigenvalues are identical, we call them degenerate. And if we continue here, so let's assume an operator A, as we just saw before in the definition of eigenvectors and eigenvalues. So the we consider this operator A in a matrix form, and we want to solve this very specific equation here. So which can also be written as A minus AI. So over this one here denotes the identity times the vector equals 0. So I is the identity matrix depending on in which dimensionality you are. That of course increases the dimensionality of the identity matrix. So the solution to A minus AI times psi or ket psi equals 0 exists only if the determinant of A minus AI equals 0. Okay, let's look at one specific example here. So we take our operator, which looks in that case like that. So we have A given by -1, 2, -4. So now what we do is we take our operator minus AI. So whatever the A is, so we take the identity matrix, which you remember is the diagonal matrix with all ones. So therefore, if we subtract that from A, we see our A's here, okay, only the diagonal. So the other ones remain the same. Now, let's look at the determinant of A minus AI, which is given by, so you take -1, the upper left element here, minus A, times the lower right element here, -4 minus A, plus so actually it is minus the other two elements. So -1 in that case times 2, but since we have -1 already here, we have a sign change, so resulting in +2. And if we multiply that out, what we get is a squared plus 5a plus 6, which then again can be simplified in a plus 2 and a plus 3. So as we know that the determinant of A minus AI equals 0, the eigenvalues are the 0 points of this equation. Okay, so in that case, it is A sub 1, so the first eigenvalue is given by -2, and the second eigenvalue, A sub 2, is given by -3. But now let's look at the eigenvectors. So how do we get that? Now that we already know our eigenvalues, it's very easy to get to the eigenvectors. So again, we start with the already well-known A minus AI, and start with the first eigenvalue, which is -2 in that case, giving us this result here. So 1 minus 1, 2 minus 2 in matrix form. So now we're going to set that to 0. So we create that systems of equations here. So 1 minus 1, and we have our psi 1 and psi 2 here. And we multiply that out. And the result that we get is 1 psi 1 minus 1 psi 2 equals 0. And 2 psi 1 minus 2 psi 2 equals 0. Okay, so now that psi 1 and psi 2 equals 1, the eigenvector is given by 1, 1, c being an arbitrary constant here, c times 1, 1, okay? And now we do the same for the second eigenvalue. The same procedure again, resulting in psi 2 equals 2 and psi 1 equals psi 2 over 2 equals 1. So therefore the eigenvector is given by c 1, 2, and again c being an arbitrary constant. So now that we know that, we may proceed and look at, so remember everything that we discussed relies on this matrix mechanics. So everything that we looked at so far is Heisenberg's matrix mechanics. And the calculation of energy niveaus in that case is identical to determining the eigenvalues of the Schrödinger equation here that we see. Remember, that's the Hamiltonian on the left, which contains potential and kinetic energy and equals the energy of that state, and the energy is a scalar in that case. And in matrix form, it's represented as we see here on the bottom, and therefore the allowed energy niveaus of these physical systems are the eigenvalues, so the energy values. Okay, but enough with that. Now, the key message about the meaning of eigenvectors and eigenvalues is, if we look at that last point here, so why are eigenvectors and eigenvalues important? So consider the eigenvector corresponding to the maximum eigenvalue. If we now take a vector along this eigenvector, then the action of the matrix is maximum. No other vector, when acted on by this matrix, will get stretched as much as the eigenvector. Okay, so that's the key important message. Now that we know that, and now that we know why we want to use eigenvectors and eigenvalues, we want to continue with C-bits and their states. Manipulating operations on C-bits is what we look at next. So the projection operator that we remember from before has no interpretation as a physical operation on classical bits. So replacing C-bit state with a zero vector does not correspond to any physical operation. However, as the swap operator S sub ij acts as identity, the states I and j are the same. So you remember, if we have the states 0, 0 and the states 1, 1, the swap operator doesn't do anything to them. So you will still get 0, 0 if you input 0, 0. But it flips the numbers if their states are different. So in that case, you can construct the swap operator out of the projection operators. And you may try that out. So it's very similar to what we already did before with adding up the matrices when we constructed the swap operator or the controlled knot operator. It's very similar to what we did there. And you may wonder why you want to do that. So if we look at a quantum computer, the physical quantum computer, these systems are inherently unstable. And anytime I have an operation that runs on multiple qubits that threatens the state of superposition more, so threatens to cause a collapse, and threatens that more than when I execute a series of single qubit operations. So the simpler my operations, the better. So therefore, sometimes it may make sense to deconstruct a bigger operator into a series of smaller ones and execute these instead of executing the large operator on multiple qubits. That's why we are interested in that. S sub ij can also be constructed out of the controlled knot operator C sub ij, and a controlled knot operator can also be expressed in terms of projection operators and knots. So here you see how you can combine these two, so do the tensor product between these two matrices, and we looked at some of the examples before. I'll show you another one quickly. So if we say, for example, we want to construct a knot operation on 2 qubits. So remember, the knot operation is given by 0, 1, 1, 0. Now, that does the job for 1 qubit, but if we want to construct it on 2 qubits or for 2 qubit state, then what we do is we create the tensor product with itself, so 0, 1, 1, 0, which gives us, if we do everything correct. So it's 0 times 0, 0 times 1, 1 times 0, 1. We have 0 times 1, 0, 0. 1 times 1, 0. We have 0, 1, 0, 0. And we have 1, 0, 0. Okay, so now we remember the 2-qubit state in vectorial form. 0, 0 is given by that one. So we apply it to that state, see what happens. So we execute it, and we see there is no match with ones in the first row. So the first one will be 0, second one equally, third one as well, and fourth one we have 1 times 1, and 3 times 0 times 0, which gives us here on the bottom, gives us 1, which is the state 1, 1. Okay, that's how that works. As always, I recommend you try that out and see if you can construct these operators by stacking here the projection and the knot together. Okay. Another operator in quantum computing that's of importance is the Z operator, which is given by the projection operators n tilde minus m, which is given by 1, 0, 0 minus 1. And it's also called a phase shift operator. So x anti-commutes with z, which means so zx equals minus xz. And furthermore, so we learned about the commutator before. So anytime operators do not commute, the sequence of application matters. Remember that. Furthermore, the 1-C-bit projection operators can be expressed in terms of here 1 over 2 times 1. So this is again the identity minus z, and same here for n tilde, which allows the expression again of controlled knot in a different way, including Z operator. And again, I recommend you give that a try and see if you can construct the C knot operator as given by this one here. Interchanging X and Z of the latter Cij operation switches the control and the target bit, and the Hadamard transformation does exactly that. It changes Cij into Cji. Okay, so the Hadamard transformation, if you remember correctly, the Hadamard transformation is used to lift a qubit, a definite state, state 0, for example, into a superposition state where you have equal probabilities of each of the states being measured when you measure the system. So maybe we should look at a quick example. So I'll show you how to do that. So we remember the Hadamard transformation is given by this one here. And we remember the definite qubit state. So let's make this correct and say we apply the Hadamard transformation to the state 0. Then we apply it to that state here. We execute the multiplication. So we do 1 times 1 plus 1 times 0 results in 1. And we have 1 times 1 plus minus 1 times 0, which also equals 1. And another way of writing that down is, of course, with the amplitudes in there, which again is this state here. Okay. And if you try that again, so if you apply the Hadamard transformation again to that state here, then you will get the original state back, meaning you'll get back 0 in that case. Some of these transformations or combinations of operators like that one and that one, they will become important at a later point. Let's just keep in mind that they exist. It's not important that you remember all of them by heart. There's always the possibility to look them up, of course. So here's some more differences to classical computing, some more operator logic, some more. So this is what we just looked at, where we look at the Hadamard transformation, the state 0. And so for 1, of course, it also lifts that into a superposition, but with a different relative phase here. So, and we remember, the relative phase matters. If you have a global phase, it matters not. A global phase gives you still the same state, but the relative phase matters. So therefore, this superposition space up here is a different superposition state than this one here, even though the sign, just the sign is different. And there is no meaningful complement in terms of classical bits. But in quantum computing, especially combined with other operations, it has significant consequences, as we will see later on. An alternative way of expressing the swap operator S sub ij is in terms of the operator z, where it is given by a combination of the identity and the z's plus some knots here, and again some z's. So I again encourage you to try out to reconstruct the swap operator as S sub ij, given that expression here on the right. If we define an additional operator y given by I x z, remembering that I is the square root of -1, then the swap operator can be expressed as a combination of the identity, some knots, the y operator just defined, and the z operator just defined. And again, I encourage you to try that one out. As we will see, these 4 here on the bottom, they're very important in quantum computing. So continuing with the 3 components that we just defined, the 3 operators besides the identity, x, y, and z, we group this into a 3 vectors whose components are the two matrices. Okay, so each of the components of the vector is given by one of these matrices. So sigma sub x is our not operation. Sigma sub y is the operator y that we just defined before, and same for z, where sigma sub z is the operator. Now we can re-express S sub ij in that form here, where we have again our identity plus ij's, or represent our qubits. So sigma I and j, where dot represents the 3-dimensional scalar product here, given by the definition here on the bottom. And these 3 components, as just indicated, they have many properties that are unchanged under the cyclic permutations of x, y, and z. They're all Hermitian. Remember what Hermitian means. I remember that star represents or denotes the complex conjugation, where we just change the sign of a complex numbers. All of them square to unity. So if you square sigma sub x, then you get unity, so the identity. And the same is true for all the others. And all anti-commute in pairs, and the product of any 2 of them is related to the 3rd one. Okay, so if we look at that, sigma sub x and sigma sub y, it anti-commutes, so indicated by that sign here, and is related to z by I sigma sub z. Okay. Together with the unit matrix 1, the matrices sigma sub x, sigma sub y, sigma sub z form a basis for the four-dimensional algebra of two-dimensional matrices of complex numbers, meaning that any such matrix is a unique linear combination of these four with complex coefficients. And actually, you may have heard about these before. They are called the Pauli matrices, so introduced by Wolfgang Pauli for describing the angular momentum associated with the spin of an electron. And these matrices will also be extensively used in quantum error correction later on. Now, back to qubits and their states, or continuing with qubits and their states.